times this omega matrix delta xi over delta x should be equal to omega pointwise at every point in phase space, and then you have a canonical transformation. Now matrices which satisfy this condition, m transpose omega m equal to omega, these are called symplectic matrices. So now the statement is that the Jacobian matrix of a canonical transformation is a symplectic matrix. Symplectic matrices are a subset or subgroup of the general set of matrices of order 2n, 2n by 2n matrices on the real numbers. And we'll see what sort of subgroup it is in a minute. But the fact that they form a group implies immediately that a succession of two canonical transformations is itself a canonical transformation. There is an inverse canonical transformation, it's invertible, and so on and so forth. So all the group properties are going to help you to understand the set of canonical transformations. Now, this relation in itself is nonlinear. By the way, this matrix omega, 0, I, minus I, 0, this matrix omega is called the Poisson matrix sometimes, or the Poisson tensor if you write down its components, little omega ij. And it's itself a symplectic matrix, as you can see, because if I put in omega transpose here, you get omega is itself symplectic. Because if you put in omega transpose omega, omega here, omega transpose is minus omega, and omega squared is minus the identity. So this relation is satisfied and it's itself a symplectic matrix. Therefore, a canonical transformation whose Jacobian is omega, the Poisson matrix, is itself a canonical transformation. And we came across this transformation yesterday. It is in fact the quintessential, if you like, canonical transformation. It's precisely the transformation which set 2 equal to p and p equal to minus p. This transformation, it's easy to check. The Jacobian of this transformation, delta qp over delta qp in 2n dimensional phase space is in fact omega. So that's the reason why this matrix plays such a fundamental role. And there's a theorem due to Darboux theorem, which essentially says that locally at any point in phase space, you can always make a canonical transformation of this kind, and it implies that the fundamental form, differential form, is dq wedge product dp, etc. Locally, you can always find coordinates such that that fundamental differential form can be written as dp, dq wedge product dp. So that's a profound theorem which has serious implications in Hamiltonian dynamics. But what I want to point out is that this very elementary example of canonical transformation that's given to you is in a sense the fundamental canonical transformation.
So what is the statement of Darboux theorem again?
Pardon me?
What was the Darboux theorem statement?
Darboux theorem says that locally in a phase space, you can always find a canonical transformation, make a change of variables such that this fundamental symplectic form is of the form summation over I dqi wedge product dpi. Let's call that some differential form omega or something like that. So the theorem says you can always find such coordinates locally at every point. And of course, once you have that, then you go on doing wedge products of this, and they're all invariants. They're all the Poincare invariants of the flow. The last of these, when you multiply, you take an n-fold wedge product of this, is the volume element in phase space. So Hamiltonian flow is a very special kind of flow, very tightly constrained from all sides. Okay. So this thing here itself is canonical, but in general we want to understand canonical transformations themselves by looking at this, saying what sort of matrices are these? Clearly these matrices are going to be some subgroup of the set of matrices which are 2n by 2n matrices over the real numbers. So 2n by 2n matrices over the real numbers. And that set of non-singular matrices is the general linear group, and we want determinant ones, so this group here. is the set of all 2n by 2n matrices over the reals with determinant equal to +1. And the set of canonical transformations, the Jacobians, symplectic matrices, is going to be some subgroup of this group, and that subgroup is called the symplectic group, and it is SP, Tn, R. So in a sense, the study of canonical transformations of an n degree of freedom Hamiltonian system is intimately linked to the study of the symplectic group, SP, 2n, R. But the question is, how many parameters does it have? And that's the cheap way of finding out how many parameters it has. And we'll do that in a minute. Now, this relation here is a nonlinear relation in M. And in general, whenever you have such relations, extracting any information from the full nonlinear relation is tough. So what one does is this method, which is very familiar in the theory of Lie groups, which is to look at the infinitesimal transformations. And as you know, we're going to assume that in a general Lie group, any element G, which is parameterized by a set of parameters, let's take them to be real parameters, T1 up to Tr, can be written as the exponential. And I'm going to assume this. In general, it's true, except for some special cases which we won't worry about. You can always exponentiate a set of generators to find a general element of a Lie group, and it's going to look like T1 plus Tr. So the idea is any general group of transformations, Lie group, parameterized by R parameters, real parameters, T1 to Tr, can be written as the exponential of T1 times capital T1, capital Tr. These are the parameters and these are the generators, infinitesimal generators of the group, because they decide the behavior of the group elements in the neighborhood of the identity. It's clear that G of 0, by which I mean putting all the T's equal to 0, is in fact the identity element in this group here. Then it's not difficult to see that if I differentiate delta G over delta Ti, any one of these guys, and set all the T's equal to 0, this is equal to T sub I. I differentiate that particular Ti, whether these guys commute or not doesn't matter, that particular Ti comes down, capital Ti, and then I set all the little T's to 0, I get the generator.
We have to first prove that symplectic group is a Lie group, right?
Yes, symplectic group is a Lie group.
That is connected to unity. Right?
Yeah, it's a Lie group.
It's a Lie group.
Yeah, sure. Yeah, the dependence on the parameters is analytic. In fact, exponential. There are technicalities like what's the covering group of this, and etc. We will not get into things like the metaplectic group and so on. I'm not going to do that here. But for our purposes, this is the basic idea. Now, once you have a thing like this, then the study of these T's essentially tells you the study of the whole group, because you can in principle exponentiate. At least you know everything about the group, that part of the group which is connected to the identity. Just as in the set of matrices On, n by n orthogonal matrices on the real numbers, say, this group contains two pieces, two sets of matrices, one of which contains all those matrices in which the determinant is +1, and the other contains all those pieces where the determinant is -1. Now these don't form a group by themselves, because you multiply two of them, you get the identity which is sitting here, but together they constitute this group. This is the connected portion of the group. And everything you say about generators and so on will tell you all about the pieces here. But all the pieces here can be found from the pieces here by multiplying by a matrix like the reflection matrix or something like that. So the Lie algebra will tell you everything about the connected components, and it's worth studying the Lie algebra, because as you can see from this, the moment I have a condition, for instance in the rotation group, I have a condition that rotation times rotation transpose equal to the identity. That's my definition of rotation matrix, orthogonal matrix, R transpose or R transpose R, they're the same for finite matrices, is equal to I. But now if I differentiate, I want to find out what do the generators do and how many there are, etc. If I differentiate this with respect to one of the parameters and set all the parameters equal to 0, then I'm going to get some Ti transpose times R at 0, which is equal to 1, plus I differentiate this piece and set the parameter 0 here, Ti, this brings down that, equal to 0 because I has no dependence on the parameters at all. So this immediately tells me that for the rotation group, the infinitesimal generators are antisymmetric matrices, n by n antisymmetric matrices, and they form a Lie algebra. So the study of the rotation group in n dimensions is simply the study of the Lie algebra of antisymmetric matrices, n by n antisymmetric matrices. And how many independent parameters are there in an antisymmetric matrix? N times n minus 1 over 2. Because all the diagonal elements are 0, the ones on the top diagonal are minuses, the ones below the diagonal. So R in this problem is n times n minus 1 over 2. So that many generators. In 2 dimensions you have just 1, in 3 you have 3, which is an accident, in 4 you have 6, and so on and so forth. That's what a general rotation does. We look at the Lorentz group, 4 by 4 transformations. You have lambda transpose G lambda equal to G. I play the same game as before. Then this generator here will be Ti transpose G. That gives you unity. That doesn't get differentiated. Plus, when I differentiate this, I get G times T I equal to 0 because that's a constant matrix. So the generators of the infinitesimal generators of the Lorentz group, 3 plus 1 dimensions, or doesn't matter how many dimensions, are those matrices which satisfy this relation here. Or if you like, Ti tilde equal to minus G Ti. And I put a G inverse on the right hand side, but G squared is 1, the identity matrix, so G itself. So all those matrices which are not antisymmetric, but which satisfy this, whose transposes are G times the matrix times G, that Lie algebra tells you the Lie algebra of the Lorentz group. You play the same game here and look at what happens. And this will help us count the parameters. This will give you Ti tilde, one of the generators, omega, plus omega times Ti equal to 0. Because this is a constant. This Poisson matrix has got no parameter dependence. I differentiate with respect to any other parameters, little 3Pi, and set it equal to 0. I get this. So the question is, how many i's are there? You need to find out. Well, that's not hard to do. Here's a cheap way of doing it. Suppose Ti is of the form sum A, sum B, sum C, sum D, block matrices, n by n block matrices. Then once clear that this will imply that Ti tilde equal to A tilde, B tilde, C tilde, D tilde. And let's impose this times omega, which is 0I minus I0. This should be equal to minus omega, which is 0I minus I0. So let's take the minus in, minus this, times T itself, which is A, B, C, D. Or it says that A tilde, minus C tilde from here, and then that's A tilde, this is 0, minus B tilde, and then B tilde, should be equal to, it goes away, minus C, and then 0, minus D, A, B. So whatever be the generator, every one of the generators must satisfy this condition, which at once tells you that C must be equal to C tilde right away, and B must be equal to B tilde. In other words, they must be symmetric n by n matrices. And the other conditions tell you that A tilde is equal to D minus D. And the conjugate of that, which is minus B tilde equal to A, which follows from this relation. Now we are ready to count parameters, because these are n by n matrices. This symmetric matrix, n by n matrix, has n times n plus 1 over 2 real parameters, because it's symmetric. This gives you another n times n plus 1 over 2. And there's no constraint on this. All this says is that if you tell me D, I tell you A. If you tell me A, I tell you D. So there's n squared pieces of information given here. So the total number of independent parameters for the symplectic group, SP, Q, and R, has this plus this plus this parameters, which is n squared plus n squared, which is n times 2n plus 1 parameters. So, yeah.
This Ti matrix satisfies this Ti tilde omega plus omega Ti is 0.
Right.
So can we say that this Ti is Hamiltonian matrix?
Is it?
Hamiltonian matrix.
What's a Hamiltonian matrix?
Some course Hamiltonian matrix was defined. I did some course. That course Hamiltonian matrix was defined to be the matrix that satisfies this.
I've heard of Hamiltonian graphs. What's a Hamiltonian matrix? Symplectic matrix. Maybe that's what is meant, a symplectic matrix. Oh,
It was defined to be Hamiltonian matrix.
I'm sorry, I'm not familiar with the terminology. Hamiltonian graphs, yes, but Hamiltonian matrix. By the way, the generator does not have to belong to the group. That's, you've got to remember that. An antisymmetric matrix, a real antisymmetric matrix, is the generator of a rotation group. It's not necessarily orthogonal. So you exponentiate it and then you get something that's orthogonal. So the generator doesn't have to belong to the group. The exponential of the generator does. Just an aside. So anyway, this symplectic group has this many parameters. On the other hand, how many parameters does SL2NR have? It's just real elements, 2n by 2n. Therefore, there are 4n squared elements. And you put a condition that the determinant be 1, right? So it has 4n squared minus 1. This is a subgroup of that. It's much smaller in some sense, fewer parameters. It's a subgroup. Of course, it has to be a subgroup of the general linear group. It's a subgroup of this group here, except in one case. And it's a very important case in optics, for example, Lie optics and so on. And that is the case when n is 1. When n is 1, each of them has 3 parameters. And you can go further. It turns out that SL2R and SP2R are isomorphic. These are exactly the same. There's 1-to-1 correspondence. So what it's saying is that the requirement that the 2 by 2 matrix with unit determinant and real entries, 2 by 2 matrix with real entries have unit determinant is enough to make it symplectic. And that has interesting consequences. But in higher dimensions, when n is greater than 1, then the symplectic group is definitely a subgroup of the special linear group. So the condition that the determinant be equal to +1 is not enough to make a matrix symplectic. You need to put further conditions on. Now from here you can also deduce what's the Lie algebra satisfied by the generators and so on, which exactly in the same way that you do for angular momentum in any number of dimensions. Exactly the same thing. In 3 dimensions, you're very familiar with the algebra. There are 3 generators, and then you have J1, J2, commutator is J3, and so on. That's the angular momentum algebra. There's a similar symplectic algebra, which we won't get into in a moment. But this tells you that the group of symplectic matrices is really what you have to study in every case. That's the group of canonical transformations. Now, let's set this aside, we'll come back to this, and ask what's meant by integrability of a Hamiltonian system. So I start with a Hamiltonian system, H of Q and P, and ask, under what conditions can I integrate all the 2n equations of motion and get closed form solutions, in principle at least? And the statement is that there is one set of conditions which are necessary and sufficient for integrability of the system. Now, we'll make it a little more specific by saying the number of degrees of freedom is n, which is finite. Moreover, I'm interested in bounded motion, not unbounded motion, so basically rotations, librations, and so on, so that the phase space is not, doesn't have problems defining action and so on. Then,
Integrability means,
yeah.
Integrability means having the solution.
I'm going to explain what's integrability in Hamilton. I'm going to say exactly what is meant by integrability of a Hamiltonian system. It's called Liouville-Arnold condition or criterion or whatever in integrability.
Does it need to be finite or just countably infinite, discrete?
Well, there are technical problems once you go to infinite dimensional matrices, which I don't want to get into. Because then, you see, if it's finite, everything is nice. If I say something like RR transpose equal to identity, then R transpose R is also equal to identity. The moment I go to infinite dimensional matrices, get the existence of a left inverse doesn't imply right inverse. If I say something is unitary, I have to say U dagger equal to I equal to U dagger U. You're familiar with this from the harmonic oscillator, right? I have a thing like A dagger A and A dagger. A, for example, has right eigenvectors but no left eigenvectors. All these complications I want to avoid. So, I'll look at finite systems. The statement is the following. It says, if there exist n independent, functionally independent, constants of the motions, motion, F1, Fn, which are nice, smooth, analytic functions of the Q's and P's in involution, which means that the Poisson bracket of any Fi with any Fj equals to 0. Doesn't say how you find these things, just says if they exist. And they must be independent of each other. That is, you can't write any one of them as a function of the others, etc. Then you are guaranteed there exists a canonical transformation. So the structure of Hamilton's equations is preserved. QP to a new set of variables, theta and I, for example. Again, the same number of variables, such that the Hamilton equations, Hamilton's become delta theta I dot equal to delta k over delta I dot equal to minus delta k over delta theta I, k equal to k of I1. So the k, the new Hamiltonian in the new variables, canonically transformed variables, is a function only of n of these variables, not the other set at all, not the new quote-unquote coordinates, but the new momenta, if you like. These are called the angle action variables. And we'll write down the harmonic oscillator, which we can integrate anyway in the action angle variables, and you'll see why it's called the angle variable. But the interesting thing is you are guaranteed that this exists. Such a canonical transformation exists. There's no clue given as to how to find it. That would be great. Then I could test and see if a Hamiltonian is integrable or not. But there's no way of finding out. You give me a Hamiltonian, I have no way of saying whether it's integrable or not, except by guessing or looking at it and seeing if it looks close to a thing which I know is integrable, etc. Or if it's an n degree of freedom system in which the Hamiltonian is the sum of individual 1 degree of freedom Hamiltonians, then it's trivially doable. Otherwise, not true. Or if there's some harmonic coupling between the different modes, etc. In most cases, that's not the case, but this is the criteria. It's a necessary and sufficient condition. This condition is very important, that they be in involution with each other. Because if they're not in involution, you can find all sorts of constants of the motion, perhaps, but they have to be in involution, which would actually imply that delta Fi transpose omega gradient Fj should be 0. These level surfaces should be orthogonal in the symplectic sense with this metric. That's crucial, because that will lead to the fact that the motion will take place on a reduced space in these action angle variables, which is essentially a torus. And on a torus, it's the only compact n-dimensional manifold which is parallelizable, the n torus. It's like locally Euclidean everywhere. You can find global maps and so on. And these the differentials of these fellows will form a basis of vector fields on it. So that's the reason for this involution. Yeah.
K is only a function of the eyes?
Yeah, that's the magic. K will turn out to be a function. Normally you would have expected it to be a function of the thetas and the eyes, but you're guaranteed it to be a function only of the eyes. Pardon? Exactly. So what would this imply? This immediately implies, as he points out, this immediately implies II dot equal to 0 or II equal to constant of the motion. It immediately implies it's a constant of the motion, whose numerical value is found by the initial conditions. So this, remember, is an invertible transformation by assumption. It's a canonical transformation. So you found n constants of the motion at once. And what can it depend on? This is obviously going to be a function. This is 0. It's sitting here. And it's some constant of the motion. So let's write it equal to COM for each I. 1 less than equal to I less than equal to I. Then put that back in here. This will imply that this quantity here, any case, is equal to some function. Let me call it omega sub I, because it looks like the derivative of an angle. So let's just call it an angular velocity. Omega sub I, some function of all the i's. Because this k is a function of all the i's. They differentiate with respect to one of them. It's a function of all the i's. But it's now constant of the motion. Because these fellows are all constants of the motion. Equal to COM. Which implies in turn that theta I of t equal to theta I of 0 plus omega I.
K itself is also constant.
Pardon me?
K itself is also constant.
Yeah, k itself is a constant of the motion. Absolutely. So it will be either one of the i's or a function of all the i's. K is some function of all the i's. That's all. Any function. And for it's clear now, immediately you begin to see that if you begin to see the hints, if you must have periodic motion, genuinely periodic motion, every variable must come back to itself in some sense. So all these omegas had better be commensurate with each other. Otherwise all the variables won't come back to themselves. If they're not, you still have integrability, but you won't have strict periodic motion. That's what will happen when you put two oscillators which are incommensurate with each other. So periodicity is a very rare thing. It says all these omegas have to be commensurate with each other. That means some resonance has to happen. And you destroy the resonance, you are in trouble immediately. Any perturbation will destroy the resonance. So that's sort of taking us back to that thing about how periodic motion is very fragile. And it leads immediately to the so-called problem of small denominators, etc. in classical perturbation theory. But this is the basic physics here, that these fellows here. One important thing to note is that these are not absolute constants. They would depend on the i's. And so does the Hamiltonian. This k is also a function of the i's. Which immediately implies that the frequencies in the problem, the natural frequencies in the problem, the omega i's, are in fact dependent on the energy of the system. Which means the oscillations would be nonlinear in general. Only in very special cases would all these omegas become constant, and then you have no amplitude dependence of the oscillation. That is essentially linear harmonic oscillator. Everything else would be nonlinear, become energy dependent. Like as you can see in one dimension, if I don't give you the x squared potential, every other power law potential is in fact nonlinear oscillation, because things depend on the actual energy. Only in the case of x squared, as far as single power laws are concerned, does this happen. Independence of the amplitude. So what does this imply? You can now detect other constants of the motion. Theta I over omega I minus theta I 0 Sorry. It immediately follows by dividing by omega I that you have this. No, sorry, I take this back. I'll come back to this. If you have more than one motion, you're going to see that the difference of these theta over omegas for the different variables is a constant. It's equal to t.